Okay, today I shall discuss the basics of superstring theory. Superstring theory. So, superstrings was invented several years ago, around some 40 to 50 years ago, with the hope of unifying gravity with quantum mechanics. Because if you use normal quantum field theory, the Einstein-Hilbert action, and you try to quantize the Einstein-Hilbert action, then you get Hamiltonians, and you try to calculate the probabilities of probability amplitudes of scattering of photons, electrons, positrons and gravitons, then you get amplitudes which cannot be renormalized, because the Einstein-Hilbert action contains all powers of the metric tensor. So, you introduce some sort of a scaling or ultraviolet cutoff or infrared cutoff to normalize it. The main reason is that gravity is a highly nonlinear theory, whereas in superstring, if you use superstring, what is a string? A string is basically a function of two elements, one is space, another is time. String sigma is the length element, space, and this is time. So, you say the string is of finite length, so it varies between 0 and pi or 0 and 2 pi to start with, 0 and 2 pi. So, it is a finite string, it may be open or closed. Open strings means it is like this, and closed string means it becomes periodic. After sigma equal to 2 pi, it comes back to itself, and tau is a time variable. So, this function of two variables, it replaces the notion of a point particle which moves along a world line. So, in particle field theory, you consider particle trajectory, this is string trajectory. In particle trajectory, the world line is a curve in 4-dimensional space time, whereas in string theory, the string world sheet is the string trajectory is a world sheet in, let us say, mu runs between 0 to d minus 1. So, it is a d-dimensional space time. So, you can view the string as, when it moves, it describes a surface, right, it describes a surface, and it becomes a tube with some cross section, or if it is an open string, it will describe its world trajectory will define a surface, open surface. Now, why did people introduce strings into to describe with the hope of unifying quantum mechanics with gravity? The main reason is that when you write down the equation, when you write down the Lagrangian of a point particle, what does it look like? It looks like, say, dou tau x mu and dou tau x mu. This becomes if you take the square root of this quantity, so this is nothing but square root of dx mu by d tau, dx mu by d tau, dx mu by d tau, and if you integrate over the trajectory from point 1 to point 2 and apply the variational principle, then you get the geodesic equations, or in special relativity you get a flat space time equation which says the rate of change of momentum is 0. You may add forces and so on. In string theory, what you do is you consider the string as, at a given time, the string is a stretched out rubber band, and you write down its Lagrangian. The kinetic energy is dou x mu by dou tau, dou x mu by dou tau, where you are using the Minkowski metric, or more generally you may use a metric of the string space time. So, if you use a curved metric, then it becomes g mu nu of x of tau sigma. So, in string theory you also take into account, so this is a kinetic energy part, and the potential energy part is dou x mu by dou sigma into dou x mu by dou sigma. So, it is just like you have a normal usual vibrating string in which you consider the Lagrangian to be the difference of the kinetic and potential energies. This is a strain tensor dou x mu by dou sigma. So, it is a quadratic form in the strain tensor gives you the potential energy due to its stretching, and when you integrate this over the whole world sheet d tau d sigma and consider the variational principle, this is equal to 0, you get the string equations, and you can use, of course, you can use a curved space time metric. So, it becomes g mu nu is a function of x tau sigma, and then you have dou x mu by dou tau, dou x mu, dou x nu by dou tau minus dou x mu by dou sigma, dou x nu by dou sigma, and then you take integral of this, and you can also have a world sheet. This is a function of tau and sigma. So, you can put in addition Of course, here you are using the Minkowski metric on the string space, that is the world sheet metric h mu h alpha beta tau sigma, that is equal to simply the Minkowskian metric eta alpha beta. So you can write, you can write the same thing as G mu nu times h alpha beta dou x mu by dou sigma alpha dou x nu by dou sigma beta, and h alpha beta is a function of tau and sigma, it is a metric on the string world sheet. This is a function of the string coordinates, and then you take root of h where h is the determinant of h alpha beta, and then you say d tau d sigma, which is d2 sigma, you write d tau sigma as d2 sigma, a 2 dimensional this thing, a 2 dimensional surface element, where sigma 0 is tau and sigma 1 is sigma. And here your h alpha beta, if you take it to be flat space, if you take the world sheet to be flat, h alpha beta simply becomes eta alpha beta, whose matrix is 1 0 0 minus 1. Okay. So you can write down the string equations by applying the variational principle to this. So you regard in string theory, in point field theory, you regard phi as a function of the particle's position, and you get write down a Lagrangian. So the Lagrangian is a function of the field evaluated at the point x, then maybe its partial derivatives at x, then it may depend on x dx integral. This is how you apply the variational principle to this to derive the field equations. Whereas in string field theory, the field is now a function of x, which is a function of tau and sigma. So you will get a generalization of the point field theory. It turns out that you can derive from string theory, you can show that if you consider the lower energy approximation to the Lagrangian, then you are able to get not only the classical field theory but also string theoretic corrections to the equations of motion. I do not want to go into too much of this, but one of the main features of quantum string theory is that if you quantize the string using the canonical formalism, and then you consider the average of the action, that means you are looking, let us say you are looking at g mu nu of x tau sigma, and then you have h alpha beta of tau sigma root minus h or root h, and then you put h of tau sigma, where h is the determinant of h alpha beta, and then you put dou x mu by dou x alpha dou sigma alpha dou x nu by dou sigma beta d2 sigma. If you require this to be invariant under conformal transformations of the metric, that means scaling transformations in which your h alpha beta tau sigma goes to some function of some e power phi tau sigma h alpha beta of tau sigma, that is you are applying conformal scaling of the metric, conformal scaling. Then you require this Lagrangian to be invariant under such conformal scalings, and then you take the quantum average of this by assuming x mu and x nu to be quantum fields, namely describable in terms of creation and annihilation operators, and you take the quantum average of this, and you require the change in this quantum average to become 0 under a conformal transformation. That is, if you apply a conformal transformation to the metric, then this gets altered by e power phi times something here, and or if you apply, okay, if you multiply this by e power phi and you require the quantum average to remain invariant, then it turns out that this equation will be equivalent to the vanishing of the Ricci tensor. Namely, you get Einstein's field where the Ricci tensor is the Ricci tensor of the G mu nu metric, namely the metric on space time. So if this is to be, of course this is already invariant under conformal transformations of H, that is if you replace H alpha beta by e power phi H alpha beta, then your H will go to e power 2 phi times H. So root of H will go to e power phi times H, and H contravariant alpha beta will go to e power minus phi H alpha beta, so that this quantity will remain invariant, namely H alpha beta contravariant root H will go to H alpha beta root H under conformal transformation. But if you require this to be invariant under conformal transformations of this metric also, that is if you multiply it by e power phi and so on, and you expand this G mu nu around the particle around the center of the string, which is a point coordinates or moment of a point particle, and then you look at the first order approximation and take the average, and you require that change to be 0 when you change this to e power, when you apply an infinitesimal conformal transformation, namely e power delta phi of x, that means this becomes 1 plus delta phi of x. So if you look at the coefficient of delta phi of x, its average value of this quantity should remain 0, should become 0 up to first order approximations. Then you can show that this is equivalent to setting the Ricci tensor to 0, where the Ricci tensor is computed for the space time metric g mu nu in dimension d. So let us so it turns out that, so what happens is that while string theory, while quantum field theory cannot accommodate gravity into its picture owing to the renormalization problems, because the Einstein-Hilbert action integral Rx root minus Gx d4x, where Rx is the curvature. If you expand this in, if you consider the metric to be a small perturbation of the Minkowski metric and expand this, you get all powers of the metric perturbation, which is, so therefore it leads to a non-renormalizable quantum field theory. So normal gravity theory, the Einstein theory of gravitation cannot be accommodated into quantum field theory due to these renormalization problems. On the other hand, gravity becomes an inevitable consequence of string theory when you assume that the string theory has conformal invariant. The string theoretic Lagrangian has conformal invariance. So gravity naturally is a consequence of string theory. That was one of the big successes of string theory. Now I shall go into some details. If you consider a Minkowski metric, you write down the equation as, you write down the Lagrangian as dou x mu by dou tau into dou x nu by dou tau minus dou x mu by dou sigma into dou x nu by dou sigma, and then you put eta mu nu, the Minkowski metric, and you write down the, for this Lagrangian, if you write down the field equations, if you call this as the Lagrangian and you write out the field equations, namely d by d tau of dou L by dou tau x mu is equal to plus d by d tau of dou L by dou sigma x mu is equal to 0, then you get an equation of the form dou square x mu by dou tau square minus dou square x mu by dou sigma square equal to 0. Then you get a two-dimensional wave equation. You get a two-dimensional wave equation for the string coordinates, and you can solve this equation, right. You can solve this equation in flats, when the world sheet is flat, you can solve it. So if you solve this equation, if you solve the two, so you can write this equation as x mu double dot is equal to x mu double dash, where a dot denotes the partial derivative with respect to the time variable and dash denotes a partial derivative with respect to the spatial variable. If you solve this equation using Fourier series, you get x tau sigma is equal to some let us call it the center of the string x mu plus p mu tau plus summation, you can put a minus I times alpha mu n by n varying over all integers and n not equal to 0 into e power I n tau minus sigma plus another term which is a function which will be beta mu n and e power I n tau plus sigma. So you have a forward, a right moving string which are functions of, in which the string coordinates are functions of tau minus sigma, and a left, it is a left moving string, and a right, it is a right moving string and a left moving string in which it is a function of tau plus sigma. It is just the fact that if you look at f of tau plus sigma plus g of tau minus sigma, this satisfies the two-dimensional wave equation. So you will get a function of tau minus sigma and a function of tau plus sigma. So you get a simple interpretation of this as the string consists of a center x mu described by, let us say, a d-dimensional coordinate, a d-dimensional momentum as for the center of the string plus other vibrations of the string around the center. So a string represents a point vibrations around the trajectory of a point particle, quantum vibrations around the trajectory of a point particle. This point particle at time t, after time t, has coordinates p mu tau, it moves along a straight line, and the string around it is represented by these vibrations, which is this. And and a good nice interpretation of string theory is that many modes, many different elementary particles can be generated by considering those elementary particles as different modes of this vibrating string. So if you call this, if you write this as delta x mu tau sigma, you can write the string coordinates as x mu tau sigma is equal to x mu plus p mu tau plus delta x mu tau sigma, and the length variable sigma goes around the string if it is a closed string or around an open string. So once you do this, you can ask how to quantize this string, quantize the dynamics of this string, This is a bosonic string, here. So how to quantize it? So you start with the Lagrangian, L, which is a function of x mu dot and x mu dash, which is half x dot square minus x dash square, where by square I mean the square with respect to the length with respect to the Minkowski metric. So when I write x dot square, what I really mean is that eta mu nu dou x mu by dou tau, right, and likewise x dash square means eta mu nu dou x mu by dou sigma into dou x nu by dou sigma. So you, and the Euler-Lagrange equations are x double dot minus x double dash equal to 0. So when I quantize this, I introduce a canonical momentum, namely I call this as p mu. P mu is a function of tau and sigma, that is dou L by dou x mu dot. Let us call it as p subscript mu, because we are taking a partial derivative with respect to a contravariant variable x mu dot. So this comes out to be equal to simply x mu dot at tau sigma. So the canonical momentum, you have a string, canonical position field is x mu tau sigma, and the canonical momentum field is tau sigma, which is x mu dot at tau sigma, and the canonical commutation relations tell you that, equal time commutation relations tell you that you should have a relation of the form, a commutation relation of the form tau sigma dash, this commutator, because it is a bosonic field, is equal to delta mu nu into delta mu nu into delta sigma minus sigma dash. So these are the bosonic commutation relations, which can also be written as x mu of tau sigma comma x nu dot of tau sigma dash is equal to I times eta mu nu delta sigma minus sigma dash. So these are the fundamental commutation relations for the bosonic string. Now you want to know how do these commutation relations translate in the Fourier series domain. So in the Fourier series domain, you remember that we had written x mu tau sigma as x mu, just let me write it clearly, tau sigma as x mu plus p mu tau plus a vibration around that minus I times summation n not equal to 0 alpha mu of n by n e power I n tau minus sigma, a right moving string. So if you calculate x nu dot, what do you get? X nu dot at tau sigma will give you p mu, or it will give you p nu plus summation n not equal to 0 alpha nu n, that n will cancel out, into e power I n tau minus sigma. That is why I use this normalization. Instead of writing an arbitrary coefficient, I write it as alpha mu n divided by n. So you get this. Now you apply the commutation relations to this. So you will get, of course, x mu and p mu are canonical position and momenta. That means x mu comma p nu is equal to I eta mu nu, and this commute, x mu and p mu commute with this. And then if you apply the commutation relations between x mu tau sigma and x nu tau sigma, and use the fact that 1 by 2 pi times summation e power I n tau minus sigma summation over n, or e power, let us call this as e power I n sigma, this is equal to delta sigma, delta function at sigma, where sigma lies between 0 and 2 pi. If you use this identity, you get a commutation relation between alpha mu n and alpha nu n, and that commutation relation can be expressed as alpha mu n comma alpha nu m is equal to eta mu nu delta n plus m, where this is delta n plus m, delta of n is 1 if n equal to 0, and 0 if n is not equal to 0. So, it is a unit impulse function. You get these bosonic commutation relations, which is just like what you have in quantum mechanics, provided you interpret your alpha nu minus n as alpha nu n star, the conjugate of alpha nu n. So, you can view the whole string as a sequence of harmonic oscillators, as a sequence of harmonic oscillators described by creation annihilation operators with satisfying this sort of a commutation relation. This is how one quantizes the bosonic string. Now, you can ask, what does the Hamiltonian look like? What is the Hamiltonian? If you apply the Legendre transformation, the Hamiltonian density H is equal to p mu into x nu dot minus L, right, and this will come out to be equal to simply half x dot square plus x dash square, or equivalently half of x mu dot plus x mu dash x mu dash. So, you get the Hamiltonian, and if you write down, if you express this into, if you write down the Hamiltonian, this is the Hamiltonian density, it is a function of x, tau and sigma, and also it is a function of x dot. You can write it is a function of p of tau sigma, and if you integrate over whole of over dc over the length of the string 0 to 2 pi, that will give you the Hamiltonian of the string, right. So, I call it as the Hamiltonian of the string, and if you express x mu in terms of the Fourier coefficients and carry out this integration for this Hamiltonian, then you will get simply that the Hamiltonian as a function of x and p at a given tau. So, it is a function of x at a given tau and all spatial variables, and position at a given tau and all spatial variables, and they will be equal to simply a constant, namely it will be equal to half p mu plus summation n not equal to 0 half alpha mu n alpha mu minus n. Of course, there is a normal ordering ambiguity in this whole thing, right. It is just like the Parseval relation that you express the energy either in the position domain, position momentum domain, or in the Fourier series domain. So, it is the Parseval equation which tells you that a quadratic form in x and p goes over to a quadratic form in the alphas in the Fourier series domain. So, there is an ordering ambiguity here, normal ordering ambiguity is present here, normal ordering ambiguity. What is this ambiguity? The ambiguity is that alpha mu n commutes with all the alpha nu m's except alpha mu minus n, right. This is minus n, and sorry, I made a mistake here. If you look at the bosonic commutation relations, x mu tau sigma comma x nu dot tau comma x nu dot tau sigma dash, this is equal to I eta mu nu delta sigma minus sigma dash. If you write this down in terms of the Fourier series coefficients, what do you get? You get minus I times summation alpha mu n not equal to 0 divided by n e power I n tau minus sigma comma summation alpha nu m by m not equal to 0. When you differentiate, this vanishes into e power I m tau minus sigma, and if you require this to be I eta mu nu delta sigma minus sigma dash. So, there is a factor of n also which will come here. So, you will get the correct commutation relations should read alpha mu n comma alpha nu m, this is equal to n times eta mu nu, delta sigma minus sigma dash. So, this harmonic oscillator annihilation operator alpha mu n and the corresponding creation operator alpha mu n greater than 0, these are the creation or annihilation operators, and alpha mu minus n greater than 0 are the creation operators. So, all the annihilation operators commute with all the creation and annihilation operators except when you put n, you replace n by minus n here. That means alpha mu n comma alpha nu minus n, this is equal to eta mu nu, n eta mu nu, and all the other commutation relations are 0. So, this means that you can regard alpha mu n as an annihilation operator with a frequency of n, right. So when you write down the Hamiltonian, of course these frequencies come are taken into account there. So what will happen is that you can describe a state of the string, a state of the bosonic string can be specified by specifying the eigenvalue of p mu, the 4 momentum p mu of the center of the string, and the state of the quantum part, namely state of the bosonic part of the string that is state of the Fock space part of the string. That means you look at, for example, you can look at a number state in which you are looking at eigenvalues of alpha mu n minus n. You are looking at all eigenvalues of this, which is the number operator, and they all mutually commute, all these individual number operators they commute with each other, but there is an ambiguity in the order. That is, you can put an alpha mu n here and alpha mu minus n here, or if you use a normal ordering, alpha mu minus n comes here and alpha mu n comes here. So there is an ambiguity. You could write it otherwise as n goes from 1 to infinity by reversing. So you choose a normal order, and you add an infinite constant here plus a, or it may not be an infinite constant. You add an a to show that there is a normal ordering ambiguity. So of course p mu's commute with mu alpha mu. So a state of the string is specified by specifying the eigenvalue of p mu along with a state of the state of these excited portions of the string. This is the state of the center of the string, and the state of the excited states of the string can be obtained by expressed, for example, by specifying the number of bosons, with different n's corresponding to the different values of the frequencies n. So n greater than or equal to 1. You can specify the state of the bosonic string in this way. Now there is another thing which is very important here. We will derive what are called the famous Virasoro equations, Virasoro commutation relations. Virasoro commutation relations, what you do is, if you look at the string, you have, let us say G mu nu is the flat spacetime metric in spacetime. So you have something like h alpha beta root minus h into x mu comma alpha x nu comma beta d2 sigma. This is the Lagrangian, and if you write, you see this, apart from treating x mu as a dynamical variable, you can also treat the metric as a dynamical variable, and it's you can add to this Lagrangian, to this action you can add the Einstein-Hilbert action of the worldsheet metric, but the worldsheet metric will vanish. You see, the worldsheet metric can be brought into using conformal transformations and reparameterizations, namely diffeomorphisms of the worldsheet of tau and sigma along with conformal transformations, namely multiplying the metric by phi. It can be brought into a form, into the standard form, namely 0 1 minus 1 0. So this is called the light cone coordinates. So if you call, for example, tau, if you call sigma plus as tau plus sigma and sigma minus as tau minus sigma, then you can write the string sheet metric as d tau square minus d sigma square, that can be written as d sigma plus d sigma minus, and with respect to that sigma plus sigma minus, this is your metric. So that if you call this as a metric in the new system of coordinates, you can always bring it into this form, because to transform the metric, how do you transform the metric from one set of coordinates to another? It is simply h alpha beta bar is equal to h alpha beta. So at tau bar sigma bar, this is h rho sigma at tau sigma into dou x rho by dou x rho bar into dou x sigma by dou x bar sigma bar, the standard way of transforming a two-dimensional contravariant at second rank covariant tensor. So how many equations are there? One for this, one for this, one for this, one for this, but this is symmetric. So you get 3 new equations, one for this, one for this, one for this, and you have how many functions? You have only 2 functions, namely you can express tau as some function of tau bar as a function of tau and sigma, and you can express sigma bar as another function of tau and sigma. You have only 2 functions available, but you have to fit in 3 variables. You have to change 3 variables, this one h1 h00 h01 and H00, H01 and H11. H21 will take care of it, H12 will take care of itself. Okay, sorry, it should not be -1, it should have been +1. Okay, it's a symmetric tensor. So 0 1 1 0, you want to bring it to this form. The third degree of freedom is the conformal transformation, namely you replace h by multiplication by e power phi h. So when you have three transformation functions, namely phi, f1 and f2, you can bring it to the standard form, which is of this form. That is because you can multiply this. If you multiply h alpha beta by phi by a scalar, then h alpha beta root minus h remains invariant. This happens only because the string is a 2-dimensional string. If it were a k dimensional string, then h alpha beta will scale to 1 by phi power k, okay, and root minus h will scale to the determinant of a k cross k matrix. You are multiplying each element by k. So sorry, your h alpha beta is the inverse of h alpha beta, right? This contravariant is an inverse, so it will scale to phi inverse times h alpha beta, and the determinant will scale to phi power k times this, where k is the dimension of the string, and that will become phi k minus 1 if it were a k dimensional space time. So this will be equal to 1 only when k is 1, or only when so this is k minus 1, and no, h is the determinant of h alpha beta, right? H is the determinant of h alpha beta. So if you replace h alpha beta by multiplication by e power phi, or multiplication by phi into h alpha beta, then its determinant will become phi power it is a k cross k. So it will be phi power k, it will be phi power k square actually, because it is a k cross k. Phi occurs in k square different places. So multiplying the first row by phi changes the determinant by phi, multiplying the second row changes it by phi. So it will be phi power k. In the case of 2, what happens is that your h becomes h alpha beta, okay, h alpha beta goes to 1 by phi into h alpha beta, and root minus h will go to phi times root minus h. That is because h goes to phi square times h, is it right? If you multiply okay, it will go to phi square h, but here you have a d2 sigma. So this quantity should remain invariant under conformal transformation. No, this will not remain invariant under conformal transformations, it will also change under conformal transformations. But if you require the string action to remain invariant under conformal transformation, you see what is happening is that you have h alpha beta goes to e power phi h alpha beta, and h, the determinant of this, will go to e power 2h, e power 2 phi, e power 2 phi times h. So h alpha beta will go to e power minus phi into h alpha beta. If you multiply h, what happens is that you get e power phi h11, e power phi h12, e power phi h12, e power phi h22, multiplying it by e power phi, and you take the determinant, then this is nothing but e power 2 phi times h. So this will go to this, and h alpha beta will go to e power minus phi. So if you look at h alpha beta root minus h, that will go to square root of this is e power 2 phi, e power phi times e power phi. So that will go to h e power minus, that will go to h alpha beta root minus h. So that will remain invariant, right? But if you look at for example a higher dimensional, let us say it is a k cross k matrix. If h is a k cross k matrix, h alpha beta, then you multiply each term e power phi h11 etc., e power phi h1k etc., e power phi hk1 etc., e power phi hkk. The determinant of this is what? Here you pull out a phi, e power phi, e power phi, e power, so it will become e power k phi, and its square root of this determinant will be this, whereas h alpha beta will scale by e power minus phi. So this will become e power k by 2 minus 1 into phi, and this will be equal to e power minus k by 2 minus 1 into phi, and this will be 1 if and only if k by 2 minus 1 is 1, k by 2 minus 1 is 0 or equivalent if and only if k equal to 2. That means only when the string is a 2-dimensional string or it has got a length variable and a time variable, only when it is of this sort will you get conformal invariance of h alpha beta root minus h. Now you can look at what are, so what will happen is that you can bring it to that form. So if you look at the Lagrangian of the bosonic string, that is half h alpha beta root minus h x mu comma alpha x mu comma beta, you can add to this Lagrangian the Lagrangian of this metric which is the Einstein-Hilbert Lagrangian, but by after a conformal you can show that in a 2-dimensional space time your Ricci tensor or your curvature tensor, your Ricci tensor h r alpha beta will be of the form simply the scalar curvature times eta alpha beta. It will be that is it will if you compute the curvature tensor, let us not include this, it will contribute trivially to the action. So if you look at the equations of motion of the metric which come by taking the variation of this with respect to the metric to be equal to 0, you will get simply that h x mu alpha x mu comma alpha x mu comma beta, okay, this quantity minus if you take the variation of this quantity with respect to h alpha beta. What is delta h alpha beta? Delta h alpha beta is equal to minus h alpha rho h beta sigma delta h rho sigma. Likewise delta of the determinant of this is nothing but h alpha beta h alpha beta h alpha beta delta h alpha beta. So if you look at delta of root h will give you simply delta of h by 2 root h, which is equal to half root h alpha beta delta h alpha beta. So if you look at the equations of motion of h alpha beta, they will correspond to setting the energy momentum tensor of the string equal to 0. That means if you call this action as S and you look at delta S by delta H equal to 0, the equation of motion of the metric, then it is equivalent to setting the energy momentum tensor of the string to be equal to 0, where the energy momentum tensor of the string is given by the coefficient of delta H alpha beta in the variation of the action. So you can also compute it in a different way. You can compute the energy momentum tensor as dou by dou alpha x mu into dou beta x mu, dou beta x mu minus L times delta alpha beta. If you call this as T alpha beta, so that T alpha, the contravariant energy momentum tensor is simply given by eta alpha beta or eta alpha rho T rho beta. So if you write down the energy momentum tensor of this, it will be a quadratic form in the partial derivatives of the x mu, and that will vanish. So the equation of motion for the metric comes out to be this. So these are called the Virasoro conditions, but this is too strong a requirement, so we assume that only the positive frequency components of T alpha beta vanish. They give you the Virasoro equations, namely that correspond in quantum mechanics. What do you do? Just as you have the Gupta-Bloor method, in which instead of replacing an operator by 0, you assume that the operator acting on a physical state is 0. So the equation T alpha beta corresponds to the classical equation of motion, but in the quantum theory it should be read as T alpha beta acting on phi equal to 0, where phi is a physical state. So that is how you characterize the physical state, and if you write down the positive components of the energy momentum tensor in the light cone coordinates T plus plus, T minus minus, T plus minus, and T minus plus equal to T plus minus. In the light cone coordinates, what are the light cone coordinates? After the conformal transformation you bring the metric to this form and you call the coordinates corresponding to this metric as sigma plus, sigma minus. So sigma plus is nothing but tau plus sigma and sigma minus is nothing but tau minus sigma. So that if you look at this metric, if you call this as H, if you call this matrix as H, then you require that okay, if you call this as if you write down this, so sigma plus sigma minus are the light cone coordinates. So if you want to compute the metric in this light cone system, what do? You put d sigma plus d sigma minus transpose then h then d sigma plus d sigma minus, right, that will be equal to simply twice d sigma plus d sigma minus in the light cone coordinates, and that will come out to be twice d tau square minus d sigma square. You remove the factor of 2. So this gives you the metric in the normal coordinate system, the usual coordinate system. So you look at t plus plus, namely the plus plus components of the energy momentum tensor obtained by transformation to the light cone coordinates, and you require that the positive energy frequency frequency components of this vanish. So if you expand your t plus plus sigma in terms of in a Fourier series, you get ln e power in sigma or e power in tau minus sigma. This is tau minus sigma, n varying over all z. And these ln's are the Fourier series coefficients. Now when you, these ln's will be quadratic forms in the creation and annihilation operators of the string, and of course you can, in the light cone coordinates it is very easy to compute t plus plus directly, because you can write down the Lagrangian of the string as x dot square minus x dash square, which is same as half x dot plus x dash dot x dot minus x dash with respect to the metric, which can also be written as half dou plus x into dou minus x, where dou plus means dou by dou sigma plus, dou by dou sigma plus, and dou minus means dou by dou sigma minus. So if you write down the equations of motion in this system, if you in sigma plus sigma minus coordinate system, you can see that this simply gives you dou minus dou plus x equal to 0, and dou plus dou minus x is 0. Of course dou plus dou minus is same as dou minus dou plus. Dou minus dou plus is dou plus dou minus, which is dou tau square minus dou sigma square. So it gives you trivially, but if you write down the energy momentum tensor in this coordinate system, what do you get? You write L as half dou plus x dot dou minus x. So so t, if you look at let us say t plus minus, this sort of a thing, that will be equal to dou L by dou dou minus x dot dou plus x minus L delta minus plus. Delta minus plus is 0, right, so this will not contribute, and delta plus plus is 1, delta plus minus minus is 1, and delta plus minus are 0 is 0. So dou L by dou x dou minus x will give you dou plus x, so that will give you half dou plus, it will not give you, I think a factor of half will not come, will it come or not? Dou plus dou minus, okay, let it come. So dou plus x, dou L by dou minus x will give you dou plus x, and you are dotting it with dou plus x. So this is what you will get, right. So t plus minus is this. So if you lower t plus using the metric eta in this light cone coordinates, what is the metric in the light cone coordinates? It is h plus plus is equal to 0, h minus minus equal to 0, and h plus minus equals h minus plus equals 1. So t plus minus is nothing but eta plus minus into t minus minus into t minus minus into t minus minus. Eta plus minus is the only non-zero component, so t minus minus is the non-zero component. Likewise t minus plus is nothing but eta minus plus, so this is t plus plus. So you do not get t plus minus with plus being contravariant and minus being covariant, that will not contribute to that will contribute to okay, that will be t plus minus. So if you look at, for example, if you look at t plus plus, or you look at t plus minus, that is equal to dou L by dou minus x or dou plus x dot dou minus x minus delta plus minus, that will be 0, that is nothing but dou minus x dot dou minus x. Likewise t minus plus will be dou, this will be half of this, so this will be half of dou plus x dot dou plus x, and t plus plus will be dou L by dou plus x dot dou plus x, which will be equal to half dou minus x dot dou plus x. So you can get all the components of the energy momentum tensor, and you require that you want t plus plus. So t plus plus is nothing but half, it is nothing but t minus plus, and t minus plus is nothing but dou plus x dou plus x. So this is equal to half dou plus x for the right moving string, for the left moving string. So if you expand this, if you write down the Fourier series expansion for x and you calculate this, the Fourier series coefficients of the product of these two, there will be a quadratic form in the Fourier series coefficients of x, and you can see that these Fourier series coefficients ln will be simply equal to something like and be summation, after taking the normal ordering into account, it will be n goes from 1 to infinity alpha mu n plus m, or in the normal ordering the annihilation operators come to the right and the creations come to the left. So you can write it as alpha mu minus m into alpha mu n plus m, or you write it in this way, you write it as right, for n going from 1 to infinity, if you write it in this form, for n greater than or equal to 1, this will be alpha m, this is ln. So this will be m going from, this is actually okay, what will come out, it will come out to be simply equal to half summation m varying over a whole of z alpha mu n plus m into alpha mu minus m. So if you write this in using the normal ordering, you can see, you can array all the, you see alpha mu n plus m will commute with alpha mu minus m whenever n is not 0, but when n equal to 0 there is an ambiguity. So you have to add an extra term here which will take into account so what will happen is that if you write this down in terms of, if you write down the positive frequency components, or you can write down the Virasoro conditions are that ln acting on phi equal to 0 for the positive frequency components n greater than or equal to 1, and also you require that the total energy which is L0, because L0 as we saw was alpha mu n with alpha mu minus n. So L0 is nothing but the Hamiltonian, okay, and L0 acting on phi should be a times phi, that means the physical state should be an eigen state for the Hamiltonian, and it should be annihilated by the positive Virasoro frequency components, of the energy momentum tensor. So you can also write your ln as half summation alpha n plus m dot alpha minus m, where the dot means with respect to the metric eta mu nu of d dimensional space time, m varying over all z. Then you compute the commutation relations between ln and lm, and this will turn out to be of the form, using the commutation relations between the alpha mu's which we discussed just some time back, alpha mu n, alpha nu m, this commutation relation, this becomes n times eta mu nu delta n plus m. If you use these commutation relations and calculate the commutation relations between these two, it will come out to be n minus m ln plus m everywhere except when n equal to minus m. When n equal to minus m, you have an ambiguity in the ordering, so you must include another term like say a n times delta n plus m here, where a, this is the normal ordering or the anomaly, this is called the Virasoro anomaly. You must include this term because when you compute the commutation relations, you will get for different orderings it will not matter as long as you see ln is uniquely defined when n is not 0, because these two commute with each other, but when n equal to 0 it is not uniquely defined, you can choose either order. So you use a normal order for ln, namely you put all the alpha m's to the you put all the creation operators to the right, or you put all the annihilation operators to the right and all the creation operators to the left. So when you compute these commutation relations, this works everywhere except when n is minus m. When n is minus m, there is an ambiguity in the specification of this, and that because either ordering you can choose in the case of when n is n minus m you get L0, but to describe L0 you can choose any order, right. L0 is the Hamiltonian. For L0 you can write as, if you put n equal to minus m you get n minus m into ln plus m, so that minus m will become minus, so it will become 2n into L0 plus something, but L0 is ambiguously defined. So you have to add a normal order correction term here. And how do you get this correction term? You look at the Jacobi identity for Lie commutation relations, namely ln comma lm comma lk plus lm comma lk comma ln plus lk comma ln comma lm. Use a Jacobi identity and substitute these commutation relations into this. If you do that and manipulate, then what do you get? You will get a n to be equal to c naught n plus c1 n cube. That means you will get the Virasoro commutation relations as ln comma lm is equal to n minus m into ln plus m plus c naught plus c1 n cube, c naught n plus c1 n n cube multiplied by delta n plus m, and you need to determine these constants c naught and c1. So c naught and c1 will come from analysis of the relations. Say you compute in a vacuum in a state where there is nothing, in a vacuum state 0 momentum and 0 high excited states, 0 center of mass momentum and 0 excited states, that is there are no bosons in the excited states, and the ground state is also has 0 momentum. If you write this as so if you compute say L1 comma L minus 1 0 0, you substitute for this, you substitute the Virasoro relations and you compute this quantity by manipulating the creation and annihilation operators, pushing all the creation to the right, so that the annihilations acting on this 0 0 are 0 and the creations acting to the right of this 0 0 are 0. If you compute this quantity, and you also compute 0 0, I think you also have to compute L1 L2 comma L minus 2, you compute this also. So you will get in two different ways, one using the Virasoro commutation relations and two using the definitions of L1 and L minus 1 by substituting their values. For example, if you write L1 as alpha minus n dot alpha, you are putting all the creations to the right, so all the annihilations to the right, so alpha n plus m, n plus 1, so this will be summation over all n varying over integers. So you cannot have say n greater than or equal to 0 you have, plus the same thing n less than 0. So if you have n greater than 0, then you are putting a 1 here, so that will annihilate the vacuum state. So this will not contribute anything when acting on the 0 on the vacuum, this portion will not contribute. What will the less than 0 happen? If you look at the less than 0 term, alpha minus n dot alpha n plus 1, n less than 0, now these two commute with each other, so I can write this also as alpha n plus 1 dot alpha minus n, n less than 0, or equivalently as alpha minus n plus 1 dot alpha n, n greater than 0, and alpha 1 annihilates the vacuum, alpha 1 annihilates the vacuum, alpha n greater than 0, that will annihilate the vacuum. So this will become simply, this will evaluate to simply 0. So you will have that C naught, if you put n as 1 you get C naught plus C1, C naught plus C1 equal to 0, C naught plus C1 equal to 0, or equivalently C1 equal to minus C naught. So the Virasoro anomaly term can be written as C naught into n minus n cube delta n plus m. So in other words, you get the Virasoro relations as ln comma lm equals n minus m into ln plus m plus C naught into n minus n cube multiplied by delta n plus m, and C naught you determine by computing L2 comma L minus 2, L2 comma L minus 2 in the vacuum by the same method. You do it by the same method and that will come out to be equal to d, you will get C naught as d by 12, where d is the dimension of the space time. That will come because you, when you write L2 L minus 2 as what, you write it in the same way, write L2 as summation alpha alpha n plus 2 dot alpha minus n varying over a whole of z. There is no normal ordering ambiguity here because all the alpha n plus 2's commute with all the alpha minus n's, because their sum is 2, it is not 0. So if you look at the positive frequency part and the negative frequency part and use the commutation relations between the alpha, you will arrive at terms like eta mu nu into eta mu nu, and eta mu nu will be what? You see, you have eta mu nu is a standard metric, right. So eta mu nu will be say something like minus 1 1 1 1 1 1 1, where 1 1 1 appears d minus 1 times and you have 1 minus 1 appearing here. So you are computing the trace of the square of this matrix, which is simply d. So this will give you simply d, that is why you will get the factor of d, and the 12 will come when you calculate these commutators in the right way. So what you get as the Virasoro commutation relations become like ln comma lm equals n minus m ln plus m plus d by 12 times n minus n cube. So we have to determine the critical dimension d. D is the dimension of the bosonic string. The critical dimension of d will come out to be equal to 26 when you study 0 norm states, that is you look at physical states which are annihilated by ln's n greater than 1 and L0 acting on phi is a times phi. These are the physical states, and the spurious states are the states which are orthogonal to all the physical states. So you can look at states which are both physical and spurious, so they will have 0 norm, and at what value of, so you construct then a 1 parameter family of 0 norm states, and you look at the critical value of d at which the number of 0 norm states becomes very large, then you get d as 26. So of course the derivation of this is a bit lengthy, but you can also arrive at d equal to 26 in a different way through what is called the ghost. You see, when you write down the equations of motion of the string, when you calculate the path integral for using the action of the string, then you have an arbitrary gauge, right, for the metric to adopt. So you have to integrate over all the metric coefficients, worldsheet metric components. So when you use a gauge fixing, namely you express your metric as some reparameterized a transformation of the standard metric using killing vectors, right. You start with the standard metric, namely 0 1 1 0 in the light cone coordinates, apply reparameterization and while scalings to arrive at an arbitrary metric. So reparameterizations are obtained by using coordinates xi plus xi minus. So that, for example, if you look at the killing form delta h plus plus, that will be del plus xi plus twice del plus xi plus, delta h minus minus will be twice del minus xi minus, delta h plus minus will be del plus xi minus plus del minus xi plus, where del plus del minus are the covariant derivatives in these coordinates. This is the change of the metric under an infinitesimal change of the coordinates. This is called the killing theorem. In general relativity, Killing's theorem tells you that the change in the metric delta g mu nu is equal to xi mu double dot nu plus xi nu double dot nu. This comes by using the standard formula for the change in the metric components under a infinitesimal under a diffeomorphism. So if you apply this to the string, you get this. So when you use the gauge fixing, namely when you integrate over all the h plus plus or over all the h plus plus, then it is equivalent to integrating over all the xi plus after you take into account the Jacobian between h plus delta h plus plus and xi plus, which is namely the determinant of delta plus. So a determinant of delta plus and a determinant of delta minus will come into the path integral, gauge fixed path integral, and these determinants can be expressed in terms of Berezin integrals by introducing ghost variables. Corresponding to the ghost Lagrangian, you will have a ghost commutation relation, and when you add the energy momentum tensor of the ghost contribution to the energy momentum tensor of the bosonic string contribution, you get a total Virasoro contribution. That is, if you add the energy momentum tensor of the bosonic field T bosonic alpha beta plus T ghost alpha beta, and then you construct all the positive frequency components of this, that will be ln of the boson plus ln of the ghost, and then you consider this as a total ln and you calculate ln comma lm, and you require again you will get anomalous terms here. So, you will get something like n minus m ln plus m plus, now you will get an anomaly. The anomaly will come due to, of course, the anomaly in the bosonic string which we just saw, plus an anomaly in the ghost string, and if you want this anomaly to be 0, then d must be taken as 26. That is, if the ghost anomaly cancels out the Virasoro anomaly of the, if the ghost Virasoro anomaly cancels out the Virasoro anomaly of the bosonic string, then that happens when and only when d equal to 26 and a equal to 1. That means Lorentz invariance should be there and the critical dimension of the string should be 26. Okay, I will stop at this point. Thank you.